Welcome back, class. As I mentioned in the last video, we talked about limits, and we talked about the vast majority of the limits we're actually going to calculate. But over this and the next section, 2.3 and 2.4, I'm going to talk about a couple other kinds of limits that will show up in other mathematical areas. First, in 2.3, we're going to talk about limits at infinity. That is, we want to talk about what happens as the input gets really big. So let me draw for you a few graphs here. And in the context of these graphs, I want to talk about this whole idea of a limit at infinity. So namely, I want to talk about what is the limit as x goes to infinity of, and I'm going to call this f of x, this g of x, and this h of x. So what is the limit as x goes to infinity of f of x? Well, that depends somewhat on your interpretation of exactly what this graph is doing. But what this is talking about is, again, thinking about an input of infinity, or an input that's close to infinity, or an input that's just really, really large. And so what I can see is as the input gets bigger and bigger and bigger, the value of this function is getting smaller and smaller and smaller. So if you think that as this graph sort of goes out, that this graph is getting arbitrarily close to this axis, then it's pretty plausible that this limit is 0. And what this means is, as the input gets really, really, really large, the output goes to 0. Now, plus infinity is over here. There's also a minus infinity that lives over here, so we can also talk about the limit as x goes to minus infinity of this function. Okay. Namely, what happens as I read the function in this direction? And as long as the trend continues, it looks like this function is going to keep getting bigger and bigger and bigger. And so if it's getting bigger and bigger and bigger, what does that mean? That means this limit is, we're going to write plus infinity. So again, what does this statement mean? This statement means that for very negative inputs, that is, inputs way on the negative infinity direction, this function's outputs are getting bigger and bigger and bigger. Now let's look at g. If I look at the limit as x goes to infinity of g of x, now here as the inputs go in the plus infinity direction, the outputs are also going in that direction. So this would be plus infinity. And if I look in the minus infinity direction, in fact, actually, it's also going to plus infinity. In both of these directions, the output is going towards the plus infinity on the output axis here. How about this function, h of x? In the case of h of x, the limit as x goes to plus infinity of h of x, that is this direction, it's actually going down to what looks like in the direction of minus infinity, again on the output axis. And so, in fact, this limit is minus infinity. Whereas the limit as x goes to minus infinity of h of x, okay, now minus infinity in the input direction is that way, but it's now going up, so it is going towards the plus infinity on the output axis. So this is plus infinity. Okay. I will note, whenever we're talking about these ideas, I tend to write plus infinity, but plus infinity and infinity are the same thing, but I'm just putting the plus to emphasize that and distinguish it from minus. Okay. These limits, that is what happens as the function goes to infinity and to minus infinity, these often go by the name end behavior. Okay. And so if a function goes to plus infinity, then that means its value keeps getting bigger, or minus infinity, it keeps getting smaller, or if the value goes to 3, then that means the graph sort of flattens out at 3. This is the idea of limits at infinity. I want to go over what happens with limits at infinity for monomials. So you might take a second and think, wait, what's a monomial? But if you know what a polynomial is a bunch of monomials added together. So a monomial is just like an x cubed or a 3x to the 7th or something like that. So I want to start by looking at what happens to x squared and x cubed. So I want to think about what all of these are. And I can think of this in my mind as saying, okay, I'm looking at the function x squared. So you can picture your favorite parabola, or you can think of what this is actually doing, which is taking the number and squaring it. And so what this is saying is if I take a huge positive input, what sort of number am I going to get out of x squared? And so huge positive input, I would get a huge positive output. And so I will get plus infinity. Exactly the same thing is in fact true of x cubed. If I take a huge positive number and I cube it, I'm going to get a huge positive number back. So huge positive input means huge positive output. So plus infinity. The difference between x squared and x cubed is going to live in what happens at minus infinity. Okay. So if I put a huge negative number into x squared, what's going to happen? What am I going to get back? And the answer is I'm going to get back a huge positive number. Why? Because when I square a negative number, I then have two negatives, and those cancel, leaving me with a positive. And so for this function, huge negative input gives me a huge positive output, which is to say that this limit is also plus infinity. Now, of course, you can think of this in terms of what you know the graph of x squared looks like. Namely, you know the graph looks something like this. And so these two plus infinities represent the fact that both tails, the one on the right and the one on the left, they're both rushing off towards the positive infinity here at the end of the output axis. Okay. On the other hand, let's look at x cubed. If I take a huge negative input and put it into x cubed, that's saying what happens if I take a huge negative input and cube it, then I'm going to get a huge, now negative number, because there's 3 minus signs. 2 of those minus signs cancel. 1 minus sign is left over. And so this is in fact going to be minus infinity. And that's because here, huge negative input, that gives me back a huge negative output. And so if you graph this, and you probably also know what the graph of x cubed looks like, looks something like this. Okay? And so in the positive direction, the output is spiking off towards the positive infinity on the output axis. And in the negative direction, the output is spiking off towards the negative infinity on the output axis. So really, the entirety of what we've been talking about so far has to do with the fact that these arrows point up, that arrow points up, and that arrow points down. That's the essence of what these limits at infinity are dealing with. These things are also monomials, so we should also talk about what happens for these limits here. Again, x going to infinity, that means I'm thinking of a huge positive input. So x is a huge positive number. If x is a huge positive number, x to the 4th is a huge positive number. And then if I multiply a huge positive number by negative 3, then I end up actually getting a huge negative number. So this is negative infinity. Now what happens if I plug in a huge negative number? If I plug in a huge negative number and I raise it to the 4th, I get a huge positive number. Again, the reason for that is because 4 is even. There's an even number of minus signs, so they all pair off and cancel. So a huge negative number raised to the 4th power is a huge positive number, but then multiplied by minus 3, it's going to be a huge negative number again. What about 7x to the fifth? So if x is a huge positive number, x to the fifth is also a huge positive number, and then times 7, still a huge positive number. If x is a huge negative number, x to the fifth is a huge negative number because 5 is odd, and so there's an odd number of minus signs, so 1 is left over after you do all the cancellation. And so this x to the fifth is a huge negative number, and then I multiply that by 7, I still get a huge negative number, and so this is minus infinity. There's one more kind of monomial I want to talk about, which is ones with negative exponents. Okay, so let's just take the simplest one. The limit as x goes to infinity of x to the minus 1. Okay. Remember, x to the minus 1 is the same thing as 1 over x. And so I'm asking, if I take an enormous number and I plug it into 1 over x, what kind of number do I get? So like 1 over 1,000,000, for example. What kind of number is that? Well, 1 over 1,000,000 is a ridiculously tiny number. 1 over 1,000,000,000 is even a tinier number. And so what is this limit actually? This limit is actually 0. Because 1 over huge is tiny. What about the limit as x goes to minus infinity of x to the minus 1? Well, now I'm taking a negative huge number. Well, 1 over a negative huge number is still tiny. It just so happens instead of being a tiny positive number, it's a tiny negative number. But that doesn't matter. This is still going to 0. If you briefly allow yourself to think about what happens if you take 1 divided by infinity, this is basically saying, imagine you want to share a pizza with your friends, but you have infinitely many friends. And so you split the one pizza amongst infinitely many people. How much pizza does each person get? Nada. So this just is 0 if you try and make sense of it. Okay. This is borne out if you think about what the graph of 1 over x looks like. Anyway, the graph of 1 over x is this thing that they made me learn for some reason was called a square hyperbola. So here's the graph of 1 over x. That probably looks a little bit familiar. And the zeros, they're coming from the fact that this piece at the end, these arrows at the end, are pointing horizontally in the direction of the x-axis. Namely, this thing is just trailing off towards the x-axis. Not quite getting there. Again, I promise I'll say this word very shortly, but if you're thinking the word asymptote, that is the right word to be thinking when I say something is getting closer and closer to something. What if I took something like limit as x goes to infinity of negative 7x to the minus 4th? Or the limit as x goes to minus infinity of this. What are these going to be? Well, remember, minus 7x to the minus 4th. That's the same thing as minus 7 over x to the 4th. So if I take a huge input, that's going to make the denominator huge, but the numerator is still minus 7. And so exactly like the x to the minus 1, these limits are both 0. In fact, any negative power of x, if you take the limit as x goes to infinity or the limit as x goes to minus infinity, it is just going to give you 0. Okay, so that should tell us how to handle every monomial, whether there's a positive or a negative coefficient up front, and whether there's a positive or a negative exponent. We now know what to do. So what about polynomials? So that is to say, what if I take something like the limit as x goes to infinity of this mess, or the limit as x goes to minus infinity of that same mess? And this seems like it's going to be messy because you know how to handle each of these pieces individually, and you might be worried about how you're going to have to put them all together. But actually, it's not very complicated, because the rule here, in the tug of war between the x cubed term, the x squared term, and the x term, it's always the highest power of x that wins. Okay, or frequently people like the word dominates. So in that case, that's this x cubed term. That means that when I calculate this limit, it works out exactly the same as if none of this was even here. Okay, so this stuff underlined in red, that stuff just does not matter at all. So I treat this just like I was looking at 7x cubed. So huge positive input, cube a huge positive number, get a huge positive number, multiply it by 7, get a huge positive number. So we plus infinity. If I take a huge negative input, I'll cube a huge negative input. I'll get a huge negative number, multiply it by 7, I'll still get a huge negative number out. Okay, so this first one was positive infinity, the second one is negative infinity. Now, before we go too much further, I want to make an important note. And my important note is, everything in this section only applies to limits where there's an infinity or a minus infinity. So nothing in this section changes anything we learned before. And it's very important that when you encounter limits that aren't going to plus infinity or minus infinity, that you use the stuff from 2.2, not the stuff from this section, because it doesn't apply to this section. So the only limits that you're ever going to apply this section to are the ones that advertise themselves very loudly by having either an infinity or a minus infinity right there in the x goes to part of the limit. Okay, that's enough for this video. In the next video, we're going to talk about how to calculate limits as x goes to infinity and x goes to minus infinity of rational functions. But that's all for now, so I'll see you next time.